Hi, I'm John Iredale, Pro-Vice-Chancellor for Health and Life Sciences here at the University of Bristol. I'd like to welcome you to the second of what we're terming our Fireside Chats, where we meet the experts who are leading the charge of the fantastic COVID research that's taking place at the University of Bristol. And I'm delighted that for our second venture into this area, my guest is Professor Imre Berger. Imre is Professor of Minimal Biology at the joint Bristol University and Max Planck Centre for Minimal Biology. He was trained as a biochemist at Leibniz and Hanover Medical School. He then went on to work at MIT and ETH in Zurich, and has, as you've gathered from that, a fantastic pedigree in molecular biology and minimal biology. Imre's current interests involve generating novel vaccines, genetic and protein engineering, and pushing forward the boundaries really of vaccine technologies using entirely novel approaches. So Imre, welcome.
Welcome, John. Thank you so much for this really kind introduction. You gave me way too much credit, but thank you. What can I do for you today?
Well, you need to tell us all about what you're up to. So I guess a good starting point might be if you could describe to us what it is about your work, how you are making these new vaccines, and then we could maybe move on to how they differ to the existing vaccine strategies that we're hearing a lot about in the media.
Well, John, you know, like much of good science, this was a coincidence. So we were working a few years back on a set of proteins, and then we came across one protein which was extremely stable and could self-assemble into a structure which looked like a virus. So all of a sudden we had this protein molecule. It was an engineered scaffold which we had worked on and designed, and it was looking like a virus, and it was extremely stable. So moreover, one could very easily engineer it. So one could engineer it in a way that you could replace bits and pieces on the surface of this virus-like particle with bits and pieces from real viruses, harmless bits and pieces, so that you then ended up with a virus-like particle which from the outside looked like a real virus but was not dangerous and was not replicating. And back then we were working on an obscure mosquito-borne tropical disease. It's called chikungunya, which is slowly spreading northwards from the sub-Saharan Africa region. And we thought that we could develop a vaccine candidate for this, and this worked very well. We published a nice paper last year in September, and said, among other things, that the scaffold which we had developed would be a great candidate for pandemic diseases, for this disease X, which would all of a sudden come and overwhelm the world. And now a few months later, here we are. We have COVID, it came, it overwhelmed the world, and we are putting our heart where our mouth was, and that's how we engaged in this. We are trying to make a vaccine to combat and defeat the current pandemic.
Fantastic. So if you like, you're creating, let's not say it's a sphere, because as you say, it's a self-assembling molecule, but it's or series of molecules in 3 dimensions. And this can then be covered using genetic engineering with the sorts of surface proteins we see on viruses like COVID. Is that correct?
That is exactly correct, John. This is what we are doing. We don't take the whole proteins, but we take the most important pieces of them, those which make a virus infectious.
And of course, those are also likely to be the pieces of the viral protein that the immune system will see, because they're the poking out bits, the bits that may help it get into cells, for instance.
The idea behind this is exactly as you say, that when the immune system sees our virus mimic, it will develop antibodies against these bits and pieces which we are presenting. And then these antibodies will be ready to bind to the virus when the real virus arrives and inhibit its entry into the cells. That is exactly what we are trying to do. This is an approach which is different from the other approaches currently pursued and fast-tracked. And we think the more possibilities we have, the better it is, because nobody knows who will be able to make a vaccine to combat this disease.
So it's clearly advantageous that in the world, actually within the UK, we've got a whole series of complementary vaccine strategies going on. Now, you've perfectly described what you're up to. Could you give us an idea of the other two major groupings? I know because we spoke to Adam in the previous podcast, Adam Finn. We are a recruiting centre for Sarah Gilbert's group's programme based in Oxford because of the close links that the various groups have. Do you want to just outline how your approach differs from the other two major groups?
Certainly I can do this, even though I'm not a vaccine specialist. As I have told you before, we came from the left field into this business.
Do we need a spoiler alert? Spoiler alert for staff. You're not a vaccinologist. No, sorry, do continue.
All right. So, I mean, first of all, one has to say that those are excellent people in Oxford and also at Imperial who are doing this work, and they have been fine-tuning their approach for 30 years. So they are really, really leading the field, and I hope and pray that their vaccine approaches work out. So what the Oxford people are doing, they use a different virus. It's called adenovirus, into which they put in a bit of the genome of the new COVID coronavirus. And by infecting the people they will vaccinate with this other virus, they will produce those bits and pieces which will then make the immune system develop antibodies. The approach by Imperial is conceptually similar. It also takes a piece of the gene of the new coronavirus and coats it with nanolipids and injects it directly into the objects, or like now animals, later then also humans, where again then proteins are made from the coronavirus, from the new coronavirus, and the immune system will again make antibodies against it. So if you compare these three approaches, then the approach from Oxford uses a different virus to bring in the genetic material of the new COVID virus. The method from Imperial uses RNA to bring in a piece of the genetic material. And we directly bring in with our approach that part of the virus which is really relevant to inhibit its entry into the cells.
Yeah, and of course what you're doing is you're bringing to the immune system protein. And of course it is protein that the immune system is fine-tuned to respond to.
That's correct, John. That is our approach.
So, I mean, given what you've described, and of course I know a bit of the background, but the speed with which your work in this field has taken off over the last few months has been extraordinary. I know it's been well supported by the Elizabeth Blackwell Institute, amongst others, and of course the universities right behind you in everything you do. But am I right in understanding you've already reached the necessary stage where you're looking at the immunogenicity in animal studies?
That's right, and I say a big thank you to everybody involved, notably the Elizabeth Blackwell Institute, because they realized very quickly that fresh money was required to push this forward. And yes, we are now in animal studies. There are things which you have to test in animals first before you can even think about going to human trials. You have to see whether the vaccine candidates you are making are dangerous, whether they are toxic, whether they are well tolerated. And so much I can already say that the mice are happy after the injections, so they are, at least for mice, not toxic. And once we have convinced ourselves that the vaccine candidates we are making work well in animals, and we have convincing mouse data, at least of the quality we had last year for chikungunya, then we can think about getting all the engines up and running and all the support we can muster to then look for going towards human trials. And we will again rely on everybody to support us, including you, John.
That's all right. I shall support you, of course I will. Of course I will, Imre. No, I think that that is terrific. It's really exciting work and holds enormous promise at this important time. Um, I final point I wanted to touch on was a little bit like Adam Finn, who we heard from last time. I'm aware that you were watching the news, you were watching what was happening in the world, and you started to reorientate your laboratory activities well before the idea of lockdown and massive changes to social behavior came in. So it'd be interesting, I think, to hear a little bit about that. And also, as the university starts to consider how it might go back to working, how you've established social distancing within your laboratory, because by definition, that's what you've had to do.
Well, we are an international team in the laboratory. I am German, so we were very carefully watching what was going on in other countries. And it was plain to see that the UK was following what was happening in Germany and France with roughly 10 to 14 days delay. So it looked a lot like the shutdown would be imminent. And thanks to the contributions and the collaborations of everybody in my lab, so that's a fantastic team we have, we could safely transit the research which we are normally engaged in the lab to a hibernation state. So our ambition there was that in the moment when we reopen the laboratory again, we can just start working as before and fire on all guns and come out of this crisis stronger than we went in. And this worked very well. So the people were very conscious about this, and my team members then performed superbly, and then slowly but steadily started to go home until we were left with a volunteer core team of people who are now doing the vaccine work in the lab and also supplying other groups in the Bristol Uncover undertaking with material and COVID-related reagents. And so now when we think about reopening again, we have to be, of course, very careful, because we do not want to risk to infect people again or de novo when we come back to the laboratory. It will be a challenge. We will have to socially distance in the laboratory. This will limit the number of people who can be in the labs at a time. We were thinking about maybe working in shifts and maybe very disciplinedly just come in to do certain jobs, and everything else like planning, computer work, all do at home. Again, the team is fantastic, so we are working with our team together to find ways already now ahead of time how we can reopen the laboratories again and how we can step by step and cautiously go back to operations, maybe not as normal, but as close to normal as possible.
Imre, that's fantastic. It's been wonderful to hear about all of your work. I think everyone in the university wishes you the very best, and of course is desperately hoping that we will see huge success come out of this work. I know you've been incredibly busy, and I'm really grateful to you to have given us this part of your time this afternoon to hear about all of the exciting activities you've been up to. Thank you so very much. And thank you, of course, to your team.
Thank you, John, and it was my pleasure.